Good day, I'm J Wildberger. In today's video we're going to talk about the SAT problem, or the satisfiability problem, and how we try to sort of circumvent or sidestep this problem with the Algebra of Boole approach to digital logic circuits. Okay, so the SAT problem is given a Boolean expression involving circle sum, which stands for or, product, which stands for and the bar, which stands for not or inversion, in variables, say a1, a2, up to an, is this Boolean expression satisfiable? Yes or no? That's the SAT problem. So what does it mean if it's satisfiable? It means that there is then some assignment of values, 0 or 1, to the individual input variables that will result in an output of the entire Boolean expression of 1. So we're asking, can we make this Boolean expression equal to 1 by choosing the appropriate values for the input variables? If we can, then we say that the expression is satisfiable, and otherwise it's not satisfiable. So if we think about the corresponding Boolean function, so if we imagine the variables a1 up to an forming a big table, and here are all the possible 2 to the n inputs to the variables, then on the right hand column we can imagine the values of this Boolean expression as a function. Okay, so for each value of inputs we have the value of the Boolean function, and the satisfiability condition is really asking, is this Boolean function 0 or not? Okay, if it's 0, that is, if it's identically 0, it means it's never satisfiable. So it's not satisfiable. And if it's not 0, well then it is satisfiable. So it's another way of thinking about what we're talking about, just a question of whether a given Boolean expression ultimately evaluates to a function which is 0 or not. It's satisfiable if it's not the 0 function. This SAT problem is a difficult and very famous problem. One of the reasons is that it was the very first problem to be proven to be NP complete. That was done by Cook in 1971, actually at the University of Toronto. Now, what does this mean? So this is a very interesting question in theoretical computer science. Not so much in pure mathematics, although it has a highly mathematical aspect. So, roughly speaking, an NP-complete problem is a problem that we can verify if a solution is correct in polynomial time. Polynomial time in terms of the size of the inputs and how much time it requires to check whether a solution is valid or not. If that's polynomial in time, then it's an NP problem. And it's NP complete if this kind of problem is somehow generic in the sense that any other NP problem can be reduced to the given one. So NP complete problems are particularly interesting because if you can figure out a way of solving them reasonably fast, then you can solve a lot of other problems also. So the challenge here is that even though you can verify that a solution exists in polynomial time, to actually find a solution in polynomial time is a big open question. Okay, so that's a major theoretical issue in computer science. And this problem, this SAT problem, is famous because it was really the first one to be shown to be NP complete. So in other words, if you figure out a very efficient way of solving the SAT problem, then automatically you become really famous, not just for that, but for a lot of other things, because your solution can be sort of converted into a solution of a lot of other problems. A lot of the work that's gone into analyzing the SAT problem restricts to a rather special class of Boolean expressions. And these are called conjunctive normal forms. And more colloquially, they are products of sums. And in the Boolean algebra world, this is a kind of an example of such a thing. Okay? It's a product of things called clauses. And each clause is a sum in the sense of a circle sum, in other words, ors, of either input variables or their negations. So in the standard literature, these are called literals. So a literal is either an input variable, like a, or its negation, like a bar. And a clause is a sum, in the sense of circle sum, or of literals. So once we have a Boolean expression in this form, then there's elaborate technology. There's actually quite a lot of different programs that are designed to take an expression like this and try to figure out whether the Boolean expression is satisfiable or not. So there's a separate question of, given a logic gate circuit, how do you express it as a product of sums? In other words, in conjunctive normal form. Well, that's also an interesting question in the Boolean algebra world, and there's something called the Satan transformation that gives you a way of taking a standard logic gate circuit and converting the corresponding expression into this canonical conjunctive normal form. Okay, so if we take that as our starting point, we can ask, all right, is this thing satisfiable? And that would mean that there's some choice of values of a, b, and c, always either 0 or 1, for which this product is equal to 1. So there's a lot of algorithms. There's Davis-Putnam algorithm, there's DLL, DPLL, Stalmark, stochastic search. There's quite a few different programs that have been written to try to address this problem. Especially when we have typically a lot of variables and a lot of clauses, where it's impossible to do this by hand and you need some automated process. Now, one thing to note is that if we're interested in when this thing is 1, since it's a product, the product will be 1 precisely when each clause is equal to 1. So trying to find values for which this product is 1 involves, in this case, 4 separate steps. We want to make this thing 1, this thing 1, this thing 1, and this thing 1 simultaneously. Now, this is not a course in Boolean algebra. This is a course in the Algebra of Boole. So I don't want to present any one of these algorithms in detail, but I do want to give you a sense of how they kind of work. Okay? So typically what happens is that we do a search in a kind of tree-like fashion. A search for a choice of variables that will satisfy the given expression. So let's stick with the expression that we have, which is a circle sum b, circle sum c, a bar, circle sum b bar, circle sum c, a bar, circle sum b, circle sum c bar, and a circle sum b bar, circle sum c bar. Notice that each one has a, b's, and c's. This one has no bars. Here there are 2 bars on a and b. Here there are 2 bars on a and c. And here there are 2 bars on b and c. So we see that this is a symmetrical expression. Whether it's 0 or not, we don't know yet at this point. So typically one of these programs might proceed like follows. We're thinking about a tree of possibilities. Let's say starting with the variable a. There's 2 possible values that the a variable can have. It could be 0 or 1. Let's say that we look at a equals 0 to start with. But if we now make a further assumption, let's say we also agree that b equals 0, then the condition that these are all 1s gives us some information. So let's have a look what happens if we sort of take these 2 pieces of information. First of all, the a equals 0 will mean that there's an a bar here, so that's a 1. So if we have 1 or anything else, that's automatically 1. So just this first condition will guarantee that this term is 1. Okay, if we're interested in satisfiability, that's good. Similarly, this clause will also be 1. So this first condition, a equals 0, guarantees that these are 1. But it doesn't say anything directly about these other terms. Okay, so like this term here, if a is 0, then 0 plus anything is just the other thing. So this would just be like b circle sum c, and this would just be b bar circle sum c bar. So if we then impose the additional condition that b equals 0, then what happens to this clause? A is 0, b is 0. How can this whole thing be equal to 1? We are forced to have c equals 1. So if we want this to be equal to 1, this forces c equals 1. Okay, so now with these three choices, this is 1, this is 1, and this is 1. And what about this one? Let's have a look. So here, A is 0, B is 0. But that means that's 1. And C is 1, that means that's 0. So here we have 0, circle sum, or 1, or 0. That's going to be 1 as well with these three choices. So, actually already just with this single branch of the tree, we don't need to go further because we have found at least one allocation of the variables which yields a cumulative value of 1 to the expression. A equals 0, B equals 0, C equals 1, and so therefore we can say that F is satisfiable. Maybe we'll just write SAT. Now, for a bigger problem, it's not so easy. So typically what you have to do is you have to work down these trees, and sometimes you get to the situation where you are no longer able to extract any information. Then you have to go to another branch or impose some more conditions. Okay. Sometimes you're going down a tree and then you come to some condition that's inconsistent with it being satisfiable. That means you have to kind of go back up the tree and erase the assumptions that you've just been making and move to a different set of assumptions. Okay. So with a small-ish example like this, we can do it by hand, but with thousands of variables, let's say, and clauses, then this can be quite a naughty problem, and you do need programs and algorithms to make it happen. Now, one of the main themes of this course is that a lot of problems, even if initially expressed with Boolean algebra, become simpler and more manageable if we re-express them with the algebra of Boole. This is a very good example of this. So we can think about simplifying conjunctive normal form by converting it into a corresponding expression with the algebra of Boole. And typically we expect to end up with something that looks quite different from the conjunctive normal form. So let's just agree on a bit of notation here. Suppose that we have a logic circuit with input variables, say capital A, capital B, capital C, and so on. Let's agree to use little a, little b, little c, and so on to represent algebra of Boole expressions. Rather general expressions in the input variables, which are the capital letters. All right, so the capital letters are the inputs, and then maybe we have a portion of a gate representing some expression, ultimately an algebra of Boole expression, and we might talk about that portion as being little a, and this other portion is little b, and so on. Okay. So the little a's, b's, and c's are more general things. They don't have to be just input variables. They can be expressions created from input variables. And we're going to showcase some identities that allow us to move from a Boolean expression point of view to an algebra of Boole reformulation. Okay? So some simplifying little formulas or identities that help us. In the notes for the course, I'm going to show you a lot more examples of this kind of thing. So let's start with this lemma here, that A circle sum B times A circle sum B bar actually equals A. Okay? So now this is an expression in Boolean algebra. It has a circle sum representing an OR. It has this bar representing the negation or inversion. And we're saying that if we convert this to an algebra of Boole expression, the whole thing simplifies dramatically and just becomes A. So A or B times A or B bar, that's the same as A. And we like to prove these things now by converting everything to the algebra of Boole. Okay, so here is the original expression, and we replace A circle sum B with A plus B plus AB. and we replace A circle sum B bar with A plus B bar plus AB bar. Now we can go one step further and replace the B bars with what they are in the Algebra of Boole, which are 1 plus B. Okay, so we repeat this thing here, A plus B plus AB, and now this expression becomes A plus 1 plus B plus A times 1 plus B. Okay, when we expand this out, we get a 1 plus B plus AB, because the A here and the A here cancel. All right, so this is the expression that we need to expand and simplify. So what do we get? Let's multiply just using the distributive law. A times 1, there's an A times B is AB, A times this is another AB, because A squared is A. Now multiply all of these three by B. We get a B plus another B plus AB. And multiply everything by AB, well, we get AB, and then this times B is also AB, and AB times AB is also AB. And now there's lots of cancellation because the two ABs drop off, the two B's drop off, and here there are four ABs, so they also cancel in pairs, and we're just left with this first entry, which is A. So purely in the Algebra of Boole framework, we've been able to verify this little identity, allowing us to go from a Boolean algebra expression to a, in this case, simpler Algebra of Boole expression. Now recall that if we have a circle sum of three things, A or B or C, that if we convert that to the Algebra of Boole, we get this rather longer expression. We get A plus B plus C plus AB plus AC plus BC plus ABC. So we'll keep that in mind. And now let's have a look at this lemma here. This says that A circle sum B circle sum C times A circle sum B circle sum C bar is just A circle sum B. And the proof is immediate if you recognize that this is just a special case of the previous lemma. What we're doing is we're thinking about the A plus B here as one entity. Okay? This is some object. This is the same object. So we have the object plus C, actually the object or C, the object or C bar, and the previous lemma tells us that's just the object itself. So A circle sum B is playing the role of A in the previous. So this gives us an expression of the, this is like conjunction of two clauses, each with three literals. Here is another little identity. A circle sum B bar circle sum C bar is 1 plus BC times 1 plus A. And I've just factored it like this just to make it a little bit easier to remember. If we actually want a Boole type expression, we would just expand this out, but I'm preferring just to write it like that. Maybe it's a little bit easier to remember. The bars here over the B and C are reflected by having this BC term here, and the A ends up with a negation 1 plus A. Okay, I'm going to leave this as an exercise for you to do, using exactly the same techniques that we've just been talking about. And here's something now that we can do by essentially combining this one and this one. So A circle sum B circle sum C times A circle sum B bar circle sum C bar. So you have to multiply this one by this one and do the appropriate simplification, and you should get A plus B plus C plus A times B plus C. And again, I'm writing it like this somehow to reflect the fact that the B and C are playing symmetrical roles. They're both barred over here on this term. And similarly, another lemma that sort of deals with other pair. This is A bar circle sum B bar circle sum C. So the bars over the A and B. Times a similar thing with the bars over A and C now. Okay, and so you can work out what that is along very similar lines, and hopefully you will get 1 plus A times B plus C. The B and C are now sort of playing similar roles. All right, so we'll leave these three as exercises for you to do. using the algebra of Boole, getting some practice in the algebra. Very simple but powerful algebra. So now I want to return to the example that we started with, which is this expression. This is an expression in the Boolean algebra world, A or B or C times A or B bar or C bar times A bar or B bar or C times A bar or B or C bar. And the proposition is that this thing reduces to, in the algebra of Boole, A plus B plus C. It's not surprising that we get a symmetrical expression because, well, the input is essentially symmetrical in A, B, and C. But there is no one and there's no quadratic or cubic symmetric expressions as well. So how do we prove this? Well, we can just use the two previous lemmas that we already have because we have an expression for this thing and we also have an expression for this thing. Okay, so I'm going to rewrite the expression for this product as A plus 1 plus A times B plus C. So a little bit differently. Before I had A plus B plus C plus A times B plus C. Now I'm just going to group them together here a little bit like this. And the last one that we had was an expression for this. That was 1 plus A times B plus C. So we have to take the product of these two things. Okay, what do we get? Well, if we take this A and multiply it by these, A times 1 is A times this will be the same thing because A squared is A. We just get A times B plus C. And now when we multiply this, what do we get? Well, times 1, we just get itself. And then when we multiply it by this, we'll get a 1 plus A and an A and a B plus C squared, which is the same as B plus C. And now things simplify because here we have A times 1 plus A, and that's always 0. Let me remind you, that's because if we expand this out, we get A plus A squared. A squared is the same as A, so we're getting 2A, which is 0. So this is 0. And over here we have A times B plus C, and that little expression is repeated over here. There's an A times B plus C over there, so those two will cancel. And what's going to be left out of this product is just the B plus C, combining with the A to give us A plus B plus C. So we can immediately go from here to here. So what we've done now is we've evaluated the original Boolean expression as a Boole polynumber. This is a Boole polynumber. At least it would be if these little a's turned into capital A's, capital B's, capital C's, etc. Okay? And this Boole polynumber that we're getting is not the 0 polynumber. Okay? In the algebra of Boole, telling whether an expression is 0 or not is obvious because it's either 0 or it's not. If it's not 0, then it's not 0. Okay? Once you have it down in the expression as a Boole polynumber, okay, this is the non-zero Boole polynumber, so it's not 0. That means that this expression is satisfiable. Okay? But it's actually telling us more than that. It's not just that it's satisfiable, it's telling us exactly what it is exactly. So this is a more complete analysis. We're going much further than the SAT problem asks us to. The SAT problem just asks us, is it 0 or not? We're going further. We're demonstrating exactly what it is in the algebra of Boole. Now, in this case, it's not hard to do. And even in a medium-sized problem where you maybe have a dozen variables and clauses and so on, something like that, your computer can still deal with this pretty efficiently. But if it's very, very big and you have thousands or tens of thousands or millions of variables and so on, then proceeding down this road and trying to aim for a complete evaluation of this Boole polynumber might be way too ambitious. So then we may have to restrict ourselves to the SAT problem itself. Is this thing 0 or not? Okay, so we've talked about what the SAT problem is and how to take a standard SAT problem expressed in the Boolean algebra framework and sort of kind of convert it to an algebra of Boole expression, thereby hopefully simplifying analysis. But what we really want to do is to adopt an algebra of Boole point of view right from the beginning. Okay, so we want to sidestep the SAT problem by not even approaching a Boolean algebra expression. If we have a big logic gate circuit, we want to express that not in terms of conjunctive normal form, or the alternative is a disjunctive normal form, which is a sum of products. It's a kind of a dual formulation. Okay. Those are the two kinds of approaches that you standardly do in a Boolean algebra situation. But what we would rather do is right at the beginning is to head towards a Boole polynumber. Okay? We don't want to go to these intermediate positions. They may be convenient in a Boolean algebra point of view, but for us they are not convenient. Okay? So we're going to take a big circuit and we're going to try to express it directly as a Boole polynumber. And we're going to use direct simplification. Here are the two crucial properties that we use in addition to ordinary grade 9 polynomial algebra. The fact that 2 of anything is 0, and the fact that x squared, or indeed any higher power of x, is always immediately reducible to x. So again, we work with these simplifications in the context of Boole polynumbers. So this is quite interesting now. We have the possibility of replacing a whole suite of quite elaborate technology that has been developed on the Boolean algebra side of things with another suite of tools which is more geared towards the algebra of Boole. And as you can see, I hope, the kinds of challenges that we have will be quite different. It's not an immediate transference to go from one of these to another. Okay? They're very different languages, they're very different mathematically, even though ultimately the difference is only between an OR and an exclusive OR. Okay? But that manifests itself in very different mathematics. And in our next video, I want to talk about how to address the SAT problem purely from an algebra of Boole point of view, sort of forgetting about the Boolean algebra point of view altogether, and just talk about what kinds of programming tools we need to make that more efficient, to be able to analyze SAT kinds of problems in the algebra of Boole context. So there's going to be some very interesting potential for programmers to make important contributions to develop the technology on this side of things. I hope you'll join me for that. I'm J Wildberger. Thanks for listening.